So this topic is called atomic structure, and the structure of the atom is something that you looked at in GCSE. Probably one of the first topics you did in year 11 was called atomic structure. And it's important to realise that things in chemistry tend to build on themselves. So a lot of the stuff at the start of this booklet you'll recognise and be quite familiar to you, and which would be nice. But as we go through the rest of the booklet, we're going to start to encounter new concepts and new bits of detail about the structure of the atom. Because it's not so much that we told you kind of lies when we talked to you about the atomic structure in GCSE, it's just that it wasn't really the full picture. So what we're going to pick up in this topic is giving you a wee bit more information, a wee bit more detail about what the atom actually looks like. But as I said, initially at least, this will remind you quite a lot of what you looked at in GCSE. So it's top of page 11, I think this is, says the atom is the smallest part of a chemical element, but atoms themselves consist of three fundamental subatomic particles. So that's the same as GCSE. We've got the proton, electron and neutron, and you're meant to know the relative charge, relative mass and their position. And you'll be glad to hear that's nothing new. The relative charge of a proton is +1, of an electron is -1, a neutron has no charge, 0, the relative mass of a proton is 1, electron still has a slightly annoying fraction, 1/1840, and the mass of a neutron is 1. A couple of points just to note. With the proton and electron, their charges, it's really important you put the 1 in there. Because what we do, when we're talking about relative charges, what we really mean is their charge compared to each other. So if you just put proton as plus and electron as negative, you're not saying how big that charge is. However, if we put proton being +1 and electron being -1, we know they've got opposite charges, but we also know those charges are the same size. 1 is the same number as 1, obviously. So it's really important you put the number 1 in there when you're writing down the charge there. Position, protons and neutrons in the nucleus, and the electron is orbiting the nucleus and shells, and it's that part of the structure of the atom we're going to build on this topic. The shells that electrons orbit in aren't exactly the same as the shells we told you about in GCSE. So that's where we're going to go throughout the rest of this topic. But anyway, the number of each subatomic particle present in an atom of an element can be calculated using the atomic and mass number. And those are two concepts we did look at in GCSE, and luckily again, they haven't changed at all. The atomic number is the number of protons in the nucleus of an atom. And then we see below there, the mass number is the number of protons and neutrons in the nucleus of an atom. So those are two important definitions, and it's sort of good to mention at this point, they're probably a lot stricter with definitions at A level than maybe at GCSE. So GCSE is probably a wee bit of leeway with how you express your definitions. At A level, they'll expect you to have these word perfect, so you can't really have much wriggle room with this. So it's really important you're really tight on learning these definitions. Just in terms of unpacking what those mean, so atomic number is number of protons. That will generally also give you the number of electrons as well, assuming you've got an atom. Now remember, we've got ions where you lose or gain electrons, but if it's just a neutral atom, because the charge in proton and electron is the same, they should cancel out, therefore you should have the same number of them. So atomic number normally gives you the protons and the electrons as well. The atomic number tells us the order that the elements appear in the periodic table. Again, this should be mentioned to you at GCSE, but you might not have picked up on it. Whilst we talk a lot about the periodic table in terms of its groups and properties and different names of groups, it is kind of still just a list of the elements in order of atomic number. Hydrogen's first, it's in with an atomic number 1, and as you cycle down, you go to helium, which is 2, lithium 3, 4, 5, 6, 7, 8, 9. So it is just a list of the elements in order of atomic number. That's important because it's the atomic number that actually defines the atom or defines the element. What I mean by that is, say we're talking about helium, it's got an atomic number 2. What that basically means is when you're talking about the element helium, all you're referring to is an atom which has got 2 protons. Similarly, if I've got an atom which has got 6 protons, the only option for it is carbon, because if it had 5, it'd be boron. If it had 7, it would be nitrogen. So the atomic number, which means the number of protons, tells you what the actual element is. Neutrons can change because you've got different isotopes. Electrons can change because you've got positive and negative ions. But the protons are always consistent for one individual element, which is important to realise. So in terms of how we use the atomic number and mass number, generally it's to try and work out the protons, electrons, neutrons in a particular atom. Just to go through maybe one example of that, if you look up sodium, Na, it's got an atomic number of 11, mass number of 23. So we can tell straight away, Atomic number of 11 means it's got 11 protons. Assuming that we've been told it's just a sodium atom and not like an ion, we can assume the electrons will be the same as well, so have 11 electrons. The neutrons you have to do a small amount of work for. Mass number is protons plus neutrons, and the atomic number is just protons. So if we subtract the atomic number from the mass number, we'll get the number of neutrons, which is 12 in this case. Another thing to touch on, just that you did cover GCSE, is just the idea of ions. So obviously, atoms tend to like to get full outer shells, and they'll achieve that by either gaining or losing electrons. In that case, they'll form an ion. If they lose electrons, they're probably metals, and that'll give them positive ions. Remember, that's called a cation. And if you've non-metals gaining electrons to get a full outer shell, they'll form negative ions called anions. So if you have Mg2+, the 2+ tells you that magnesium has lost 2 electrons, so must have 2 less electrons than protons, so 12 protons compared to 10 electrons. The neutrons won't change. So at the bottom of the page you'll see a table. Now this table will kind of look a wee bit familiar to you. You saw questions like this in GCSE where you're given some particles which you haven't been told the elements, what they are. You're given some information about protons, electrons, neutrons, mass numbers, etc. And you have to fill in the blanks. So it's just the same as before, it's not actually any different. So just be careful. I'm going to do maybe one for you here. We might have a couple of different isotopes chucked in here. So I'll show you what I mean. I think the first one is an example of that. So if we look at A, protons 19, electrons 18, neutrons 19. So let's look at what we can work out by that. Well, first thing I'm working out, if it's got 19 protons, that must be the atomic number, because that can't change. It's always the same as number of protons. Mass number would be the protons plus the neutrons. So 19 plus 19, which is 38. Charge would be the next thing I'd fill in. So we've got 19 protons, 18 electrons. So there's one fewer electrons than there are protons. So we're missing one. So if you've lost an electron, you're going to have a plus charge. It's just a plus. Again, same like GCSE, if it's just a 1 plus or 1 minus, generally you don't put the 1 in. Only if it's like a 2 or a 3, you put it in. Then we get the idea of the symbol, and that's the thing I want you to be careful about in this table. So you'll need your periodic table for this. So I'm looking for something which has got an atomic number of 19, because remember that defines what the element is. If I look at my periodic table, I find 19 is potassium. Now, the one thing I need to be careful about here, it is potassium. Look at the mass number though. Mass number of potassium is normally 39. And what we've worked out, this mass number here is 38. It doesn't necessarily mean we've done it wrong. It just means that this might be one specific different isotope of potassium which is allowed. Different elements do tend to have different isotopes which are very close to the mass number on the periodic table. So it is just potassium, but to show the person reading it what specific potassium it is, if it has a different mass number, we normally do the mass number up to the top left. So it'd be K38 as opposed to K39. The only thing I need to put in the symbol as well, it has got a charge, so the charge must go there as well. So you end up with K38 with a plus charge. So at this point, I probably want you to pause the video, have a quick go, so you will need the periodic table to try and work out what the elements are. See if you can fill in this table, and then I'll show you it filled in a wee second, and you can compare your answers. So hopefully this looks something like what you've got. Again, I hope I haven't made any mistakes here. It's possible I have. For something I found, the table wasn't explicit about what specific isotope or what specific mass number you had to get. For example, I think D just gave you 6 protons, 6 electrons. So it's kind of up to you what carbon you pick. So probably just pick the most common one, carbon 12. But the other ones should have been clear about which particular mass number it had. So hopefully you find that okay. Again, reminiscent of GCSE kind of work, maybe a wee bit trickier with different mass numbers, different to periodic table. So we'll finish off this first little section by looking at just at isotopes, which we've hinted at already. So again, isotopes, something you looked at in GCSE. Again, they have not changed one bit. Isotopes are atoms which have the same atomic number but different mass number, which of course means that they have the same number of protons, because they have to have if they're going to be the same element, but different number of neutrons, so the mass is slightly heavier, slightly lighter. The classic example we would use for showing different isotopes is chlorine, because it's got 2 very common different isotopes. Lots of elements do actually have isotopes. It's not just chlorine. It's just that lots of them, it's got one main isotope with like 99%, and all the rest are very uncommon. Chlorine's very unusual in that both isotopes are actually reasonably kind of abundant. Chlorine 35 is 37 or 75%. Chlorine 37 is 25%. So they both kind of exist in reasonable quantities, which is why they often come up as an example of isotopes. So if you were saying those different isotopes, you'd refer to them as chlorine 35 or chlorine 37. If you're writing down their symbol, it's just like we did before, chlorine with a 35 up to the top left and chlorine with a 37 up to the top left. So that's how you say it, and that's how you write the symbol form of it. Question is posed, how many protons, electrons and neutrons do they have? I mean, that's just exactly the same as what we were doing before. So just to fill that in. So chlorine 35, it must have, just off the periodic table, 17 protons. Assuming it's neutral, it's got 17 electrons as well. And we subtract the mass number, the atomic number away from the mass number, we end up with 18 neutrons. In contrast, chlorine 37, so we should expect the protons to be the same because that makes it chlorine. Electrons should be the same as long as it is a neutral atom, but in this case we got a couple more neutrons, we got 20 neutrons. The implication of having different isotopes isn't actually that major because it says the chemical properties of isotopes are actually identical. So if we're doing chemical reactions, it doesn't actually matter which chlorine you've got in the reaction, they should behave exactly the same. The reason for that is just that neutrons aren't that important in chemistry. Obviously they're important for keeping the atom stable, but they don't really affect the chemical properties. So neutrons don't affect chemical properties. And if the neutrons don't affect the chemical properties, the only other things that will affect chemical properties are protons and electrons. And if you see the two isotopes here, they've both got 17 protons, they've both got 17 electrons. So in that regard, they are pretty much the same. So they have the same number. Protons and electrons. So one more wee bit to kind of look at there. One unusual element with different isotopes is hydrogen. So this will be completely new to you, but it's kind of just like a wee fact. It's not actually too crucial. Hydrogen sometimes comes up in exam questions in terms of isotopes. There is actually 3 different isotopes of hydrogen. There's the main one, which is hydrogen with a mass number of 1, which has got 1 proton. You also can have hydrogen with mass number of 2, which nucleus has 1 proton and 1 neutron. And you can also have a hydrogen with a mass number 3, which is 1 proton and 2 neutrons. So again, these two are quite rare, but they do exist. The main one is the one with 1 as the mass number. Hydrogen is a little bit unusual in that scientists generally give those different isotopes different names just to make them stand out. There's no particular reason why they pick on hydrogen. Hydrogen 1, which is the normal one you look at, is called protium because it just has 1 proton. Hydrogen 2 is called deuterium, deut meaning 2, and then hydrogen 3 is called tritium because tri means 3, with the mass number being 3. So that's not really going to come up as a question in itself, like what's the name of hydrogen 2. It's just you might need to recognise deuterium as a name or tritium as a name, just if it comes up in a question. And the last little point, just about like the masses of elements. It says mass spectroscopy, which we'll look at a little bit later on, reveal that atoms of the same element could have different masses due to variation in the number of neutrons. That's just what isotopes are. The observed mass and the recorded in the periodic table is a consequence of the abundance of each type of isotope. What we basically mean is, you probably remember the example from GCSE. When we look in the periodic table for chlorine, we see 35.5 as the mass number. So that decimal place mass number just comes from the idea you've got different isotopes, and you're calculating the relative atomic mass, which is the average of those different mass numbers. So what we'll look at in the next video is just going through how we calculate that relative mass and also different ways to describing relative mass.